All right, y'all, going to be covering homework 4 here, going back finally to cover homework 4. Now that we've got the basic stuff out of the way, the decimals, the fractions, the integers, we can go ahead and kind of move on to some of the a little more theoretical stuff, I guess. So homework 4 is Intro to Number Theory. You got to be a little careful here. Number theory, if you Google this, number theory is a very advanced sect of theoretical mathematics. We're really dipping our toes in it here, and this will be stuff you've heard of before, just maybe the application will be a little different. It's nothing crazy, but it is technically number theory, so just go ahead and get that out of the way. But to let you know what the main ideas are, just to keep it a little more grounded, the first idea is prime numbers. This is what we're going to be covering today, prime numbers. The second idea is the GCD or GCF. You may know what that means already. And the last one is the LCM, excuse me, or the LCD. All right. So those are the 3 ideas in number theory. So if you're going to use Google or another website, make sure you're looking up the right things: GCD, LCD, GCF, LCM, and the prime numbers. Don't just type number theory into Google. You're going to get all kinds of results if you do that. So let's start with the prime numbers. You probably already know what these are, but just a quick refresher. All right. The prime numbers, I don't want to go too far into it here, but these are actually considered very special, very unique numbers. There's a lot of mathematicians that spend their careers studying these numbers. They're the set of numbers that have nothing that divides into them other than 1. 1 does not count because it technically has to be 2 numbers. So if you took a number and you said, what goes into this number? And you said 1 and itself, then it's prime. Sounds like 1 should fit the bill for that, but it just doesn't by definition. It has to be 1 and a different number. So we take the number 1, and 1 is the only number that goes into it. So by definition, that's not prime. What about the number 2? 1 goes into 2, 2 goes into 2, and nothing else does. So that would make 2 prime, right? 3, what goes into 3? 3 goes into 3 once, 1 goes into 3 once, and that's it, right? So what we're looking for with prime numbers is numbers that don't have anything else that goes into them. Again, remember, 1 is not prime by definition. A lot of people feel like 1 should be a prime number. Maybe it should be, but it's not by definition. 4, what goes into 4? Well, 1 goes into 4, 4 goes into 4, but 2 goes into 4 as well. So 4 is not prime. If you can find any number that goes into that number other than 1 and itself, it is not prime, right? 5, what goes into 5? Nothing but 1 and 5, so that is prime. 6, well, 2 goes into 6, so 6 is not prime, right? If you can find any number that goes in there other than 1 or itself, it's not prime. And that's what the prime numbers are. They're just all the numbers that have no divisors, meaning something goes into them cleanly other than 1 in themselves. 7 is prime, right? 8's not prime because 2 goes into it. Can't we just go ahead and start marking off every even number? If it's even other than 2, 2 goes into it. Therefore, it's not prime, right? Remember, prime numbers have nothing that goes into them, nothing that divides into them other than 1 and themselves. So what about 9? 9's out. 9's not prime because 3 goes into it. 10 is out because 2 goes into it. 11 is prime. Nothing goes into 11 other than 1 in itself. 12 is out because it's even. And, so forth and so on. 13 is prime. 14 is out. 15 is out because 2 goes into 14, 3 goes into 15, and so on, okay? So that's how the prime numbers go. You can either memorize these or you can just kind of do what I was doing, go through the numbers, each one, and ask yourself, is 16 prime, is 17 prime, and so forth, okay? Just to go ahead and list out the first common primes, it's 2, 3, 5, 7, 11, the same ones we picked up here, 13, 17, 19, 23, and so on. And if you're asking yourself why I skipped some numbers there, we'll check them. Take 21. Does 21 prime? No, because 3 and 7 go into 21. Remember, a prime number is a number that is only divisible by 1 and itself. So where do these stop? Well, they don't. And that's, again, I don't want to go off about this too much because it's not really in the scope of the class, but prime numbers don't stop. They never end. There's a way to prove it. It's fairly complicated, but they've actually proven that there's infinitely many prime numbers. We've also been able to prove that use the word prove a little loosely here, but so far it has been shown that there is no pattern to the prime numbers. It's not to say no one will ever find one, but there is no pattern here. It looks like they're skipping every other number, and then all of a sudden it skips a couple of numbers. Then it's skipping every other number, and then it skips a couple of numbers. And it doesn't do it dependably. Scientists have spent their whole life studying the prime numbers and well, their careers anyway, and never found a way to predict the next prime or to know what the pattern of them is. So they're a little strange. If you're interested, you can look that up online, do a little side research. Prime numbers are strange numbers. There's a lot to them. So, but for the scope of our course, you just need to be able to identify them. Maybe, know how to find them. I think there's one problem in the homework that asks you to list all the primes up to 100, and then it gives you some multiple choice options. I've given you a lot of them already. So, try that out. Get familiar with the prime numbers. It's really more just a definition you need to be aware of, okay? So what are we doing with prime numbers? Well, what we're going to ask you in the homework on a base level sometimes is, hey, is this number prime? And we don't, we're not just going to say list out all the primes, although I think there is one question that does that. It'll just say, is this number prime? So let's take the number 42. And they're going to ask you, is this prime or is it composite? Composite meaning it's made up of other numbers. So basically composite means not prime, okay? If it's not prime, then it's composite. So if they take the number 42 and they ask you, is it prime or composite? How do you know? Well, hopefully this one's pretty clear. This one is composite, not prime. Why? Well, think about all the things that go into 42. 2 goes into 42, right? 21 goes into 42 because 2 times 21 is 42. Think about our little check with the threes, right? We did this a couple lessons ago. 4 plus 2 is 6. 3 goes into 6. So 3 goes into 42, right? And there's more numbers than that. But the fact that I knew any number that went into 42 other than 1 in itself makes it composite. So the fact that it was even immediately tells me it's composite, right? Because the only even prime number is the number 2. Any other even number is not prime because 2 divides into it, so it's composite. What about something like 91 though? This is one where a lot of people will say, well, it's prime. And I'll ask them why. And they'll say, well, because, I don't know anything that goes into it. Just because you don't know anything that goes into it doesn't make it prime. It might be, but you're going to need to be a little more careful here. Remember what we're checking. Is there any number that goes into 91? So if you don't know, if you look at 91 and you say, well, I don't know, you have to do a little bit of a check here. Let's kind of do the same thing we did a minute ago. When we went through and asked if a number is prime or not, let's go through and see if these numbers go into 91. If I find anything, it's composite, meaning not prime. Does 2 go into 91? No, because it's even. 91 is not even. 2 is, so 2 does not go into 91. Does 3 go into 91? Well, think about the trick we talked about with threes. And you can probably tell it doesn't because 3 times 30 is 90, and you're not getting a 91. But 9 plus 1 is 10. 3 does not go into 10, so 3 does not go into 91. 4 does not go into 91 because it's not even. If 2 can't go in, 4 cannot go in. 5 does not go in because it doesn't end in a 0 or a 5. We don't bother with 6 because 2 didn't go in, so 6 won't go in. 7. I don't really know, right? This is the first one we come to where we say, I don't know. I don't think 7 goes into 91, but I don't know. You're going to have to try it. You may just have to take the number, and you may just have to try it. 7 goes into 9 one time. 1 times 7 is 7. Subtract. Bring down. Hopefully you're getting comfortable with this by now. 7 goes into 21 13 times. So 7 divided into 19 13 times. 7 goes, or not, I said 19. 7 goes into 91 13 times. So 7 goes in, and if we kept going, we would have found that 13 goes into it. So this is also composite. Because 7 goes into 91. I think I might have said 19 a couple times. Hopefully I didn't. 7 goes into 91, and 13 goes into 91. Little bit dyslexic, guys. You probably picked up on it. I tend to sometimes say numbers backwards and things. If you catch me making a mistake, for sure let me know. But if you just see me say something backwards, just kind of chalk it up to that. So 91 is composite because 7 and 13 go into it. So again, for a number to be prime, nothing goes into it other than 1 or itself. How do you know? Well, you can kind of do it in your head like we did 42. We said, well, 2 goes into it, so immediately composite, not prime. 91, we didn't really know. We had to do kind of a check with a series of numbers, and we eventually found a 7 and 13 went in. How high do you need to go? If you checked up to 19 or 23, I think you'd probably be okay for this class. Technically speaking, you'd really have to check every number up to 91 or most of them. But in this class, if you check, numbers 1 through 23, you're not getting anything, it's probably composite. All right. So again, prime and composite, not really the focus of the homework, but they're required skills and definitions you need to know. You're going to see what we're going to be doing with these here in just a moment. All right. So make sure you're cool with that. Make sure it makes sense, and we'll move on to the next idea. All right. This is where the kind of the main work of the homework will kick in. Because again, you do need to know what a prime number is. You need to know how to tell if it's prime or composite. But the main thing we're going to be doing with primes, and this is still under the concept of primes here, is called prime factorization. This is important. Don't lose this, because this is going to come up later in the course. This is important. Prime factorization. So we know what a prime is. We just talked about that, prime numbers. What does factorization mean? Well, it's the key word here is factor, which means be careful and make sure you hear what I'm saying here. It's a number that divides in cleanly. You could also say it's a number that multiplies to make that number, which means it divides into that number. Let me give you a quick example. This is not what we're going to be doing in the homework, but just to make sure you understand the idea of factorization. Let's say I asked you to list out the factors of 8, right? We have the number 8, and I want you to list out the factors of the number 8. Well, think about the factors. Factor means a number that divides into it cleanly. So 1 goes into 8, 1 and 8 go into 8, 2 and 4 go into 8. All 4 of these numbers are factors of 8. They're numbers that divide cleanly into 8. Sometimes people will go back and say, these are also the numbers that can multiply to make 8. That is true as well. So be careful how you do this. It's not what does 8 multiply. We're not talking about 16 and 24. Factors mean break the number down and tell me what numbers go into 8. 1, 2, 4, and 8. Those are the factors of 8, okay? But be careful, because we're not just listing out generic factors. That's not the point of this homework. This is prime factorization. So what we're doing is listing out the numbers that make the prime numbers that can divide into something cleanly, right? Think about what I just said. We're listing out the prime numbers that divide into something cleanly. That's the idea here, okay? So you've done this before. You just may not realize this is what it's called. So let's ask you to prime factor or find the prime factorization of the number 12, okay? A lot of people like to do this with the little tree diagram. And what I'm asking you is what divides into 12? So if it's easier for you to think about it as what multiplies to make 12, that's the same question. So we could say what? 4 and 3 make 12, don't they? And we'll talk about what if you use 6 and 2 in just a minute. So 4 and 3 make 12, and 3 is prime, so we're good there. That's what we're looking for, primes that divide into the number cleanly. But 4 is not prime, and that means that 4 can be broken down further. So we broke down 12 into 4 and 3. 3 is prime, so it will stay. 4 can break down into other numbers that divide into it cleanly, which would be 2 and 2. So 4 is gone now, which means 2 is prime, and 2 is prime, and these are the prime numbers that divide cleanly into 12. Now again, it's not just which 2 numbers. You say 3 goes into 12 and 2 goes into 12. But it's what are the factors? How does it break down? That's what we're doing. That's what prime factorization means. So if you were asked for the prime factorization of 12, you'd say it's 2 times 2 times 3. You could also write it as 2 to the second times 3, because isn't that what a exponent means? So this is the answer here. 2 times 2 times 3 also could be written like this. I don't care which way you write it. Either one of these is fine for me on the exam. So not a big deal. You just break the numbers down until you can't break them down any further, and then you collect them all back together, and those are your prime factorizations of that number. What if you broke it down a different way, though? People ask that a lot. They say, all right, well, 12, but what if I did 2 and 6? 2 times 6 makes 12. Well, 2 is prime, so we can go ahead and collect that one and stop. 6 can break down, though, into 2 and 3. 6 is gone now. We have a 2 left over. We have a 3 left over. So what we had was 2, 2, and 3, which we already said was the answer. You get what I'm saying? So the nice thing about this is, and that's why a lot of people find prime factorization to be pretty straightforward. I don't use the word easy. I don't like that word, but simple, I guess, meaning there's not a lot of steps to it. It doesn't matter how you break the number down. I used 2 and 6 as my starter breakdown. I got the same set. I used 4 and 3 as my breakdown, and I got the same set. That's the beautiful thing about prime factorization. How you break the number down is honestly fairly irrelevant as long as you're doing it with legitimate breakdowns and not just making stuff up. Let's try another one. Let's try to find the prime factorization, and know that term too, because on the test, it might ask you, what's the prime factorization of 72? It's not going to say, what's the tree thing, right? Do the tree thing. Be careful. That's what most students call it. They'll say, oh, the tree thing. Yeah, but that's not what the test is going to call it. So be careful. Know the name here. So prime factorization of 72. You break this down any way you want to. Any two numbers you know that go into 72, you can break them down with. I think the classic one is probably 8 and 9. It is not the only option. 12 and 6 would work as well, right? There's other options. But we'll go with 8 and 9 because that's what most people would use. 8 breaks down, because again, remember, we're looking for primes. You can't stop if the number's not prime. 8 breaks down into 2 and 4. 2 is done, so we can kind of just put a mark there and leave that, because 2 doesn't break down. You could break it down into what? 1 and 2, but then you just have 2 again, and 1, we're not super concerned about 1 going into things. 1 goes into everything. 4 I can break down again as well into 2 and 2. So far, 8 broke down into 2 and 4. We kept the 2. The 4 broke down into 2 and 2. 1, 2, 3 2s so far. 9 breaks down into 3 and 3. 3 is prime. 3 is prime. And so we're left with nothing but prime numbers. Collect them all together, and you have the prime factorization. Got to squeeze it in there. Of 72. 2 times 2 times 2 times 3 times 3. And if you're unconvinced about the way it breaks down, break it down with another set of numbers. Use 12 and 6, and you're going to get the exact same numbers. Okay? Because you can even see it in here. 2 and 2 is 4, and 3 is 12, and 2 is 3 is 6. You can see the numbers in here, sort of, if that makes any sense. So my point to you is, try the breakdowns, see if you can get what I'm getting, and if you use the different set of numbers to get there, that's fine. It doesn't matter how you do the prime factorization. Just make sure that your answer is agreeing with mine, and of course the homework's when you get to the questions that matter. All right, so take a minute, catch up on that. In fact, like I said, if you want to break 72 down a different way to just prove it to yourself that it's going to come out the same answer, try that, and then we will move on. All right, so that's prime factorization. It can get a little ugly. Let's actually do one more. Let's do one more with a little bit bigger number. Let's do one with a little bit bigger number. I mean, they can get, there's some in the homework I think they're a little bit larger. They'll give you some, it'll take a little time to break them down, but let's do one more. Let's go ahead and do 152. I want the prime factorization of 152. So imagine you were on the test and this is what I asked of you. Think about how you'd start this, because that's the thing. A lot of people don't know anything that goes into 152. They don't know they don't know anything large anyway. They'll say, well, the only thing I know that goes into 152 is 2. Well, then 2 is where we're going to have to start. So we got 152 here. We're going to break it down with 2 and something else. I don't know yet, but I know 2 goes into it because it's even, right? So if you need to, off to the side, do your division. I mean, it just depends on how much of this you can do in your head. 2 doesn't go into 1, so we'll move over. 2 into 15, 7 times. 7 times 2 is 14. Subtract, get 1. Bring down 12. 2 into 12, 6 times. Hopefully, you guys are getting a little more comfortable with the long division now that we did all the decimals and stuff. So 2 and 76. You don't have to know this stuff off the top of your head. And you say, well, okay, 2's good. What goes into 76, though? I don't know. Well, 2, right, because it's even. So we'll just do 2 again. If you got to chip it away with little numbers, then that's what you got to do. 2 goes into 7 3 times. 3 times 2 is 6. Subtract 1, bring down. 2 goes into 16 8 times. So that gives me 2 and 38. These are not numbers I'm super familiar with, which is probably why I didn't look at 76 and just say, oh, well, half of that's 38. And we realize, well, we can go again because 2 is prime, but 38 breaks down. So sometimes you just have to, kind of go at these in small chunks. 38 divided by 2. Well, you could try doing this in your head if you want to do it out with long division, your choice. 2 goes into 30 15 times though, right? And 2 goes into 8 4 times. 15 plus 4, 19. Again, how you get there, up to you. If you just want to divide it out, that's fine. So now we got 2 and 19. 2 is prime, and so is 19, isn't it? Because what goes into 19 other than 1 and 19? So even on numbers where you're not clear about what goes into them, you can just kind of hammer them away with 2s and 3s and 5s, sort of like we did back with the fractions when we were reducing them, right? So for the answer now, be careful. The answer to this is 2 times 2 times 2 times 19. All right. That's the answer. That's the actual prime factorization. Don't just leave the tree. You need to answer the question. You had 3 2s and a 19 to make the prime factorization of 152. Okay, so that's prime factorization, just the tree method, just breaking things down with multiplication, or it's division, however you want to look at it. I mean, you could say 2 times 76 makes 152, but the way we got 2 and 76 was with division. So be a little bit careful here, guys. Make sure this is making sense to you. We'll go ahead and move on to the GCF and GCD. All right, so now we're moving on to GCF. GCF, also known as GCD, stands for the greatest common factor. Now remember what we said a few minutes ago about what a factor meant. It also means what divides into a number, and that's what the D can be used. Instead of factor, sometimes people will say greatest common divisor. It does not matter. They're the same word. It means the same thing. It doesn't matter which one you choose to use. I usually will say GCF, but you might hear me say GCD instead. These are the same thing. GCF and GCD are the same thing. It's the same word. Greatest common factor, well, a factor is something that divides into it, so greatest common divisor. So basically what we're going to be doing is giving you 2 numbers, and let's just go ahead and put the numbers down on paper here. 36 and 24 maybe, for example. And I'm going to ask you to find the GCF or the GCD of these. Now, what's the point of doing this? How is this number theory? Again, kind of like I alluded to early in the video, number theory is a very deep concept. So GCF and GCD are actually used in advanced upper level mathematics, even though probably to y'all they seem like little trivialities. Like, oh, well, what's the greatest number that goes into both? Why would I care about that? Well, it does have applications in higher theoretical mathematics. Just, be aware of that, even if you're not aware of what the applications are. It's not a triviality. This is actually really important stuff. So, greatest common divisor of 36 and 24. What goes into 36 and 24? And I want the greatest number. So you could try to do this in your head, but some of the numbers are going to get big, so I wouldn't. We'll try it real quick just to kind of do it, but we'll talk about the method in a second. 2 goes into both, right? But is that the greatest number that goes into both? Common, meaning goes into both, and divides, meaning, divides into them. 2 goes into both, but I think 3 goes into both, so 3 is currently my greatest candidate. 36 and 24. I think 4 goes into both. You see what I'm doing? I just keep picking numbers until I get the biggest one, but what is the biggest one? Is it 4? 6 goes into both, right? So that's the thing. You sit here and guess, and eventually you might say, oh, I think it's 6. What if it's bigger than 6, though? What if you missed one? Because the thing is, I want the greatest common divisor. Not just any common divisor, I want the greatest. Well, the way we're going to do this is through prime factorization and a set of rules, okay? Once you learn the rules, it's not too bad. But until you learn the rules, this can be confusing. So I'm going to write them down. Luckily, there's only 2 of them. And this will make more sense in just a second. Let's go ahead and get the rule written down, and then I'll show you how to use it. The first rule is when you're doing the greatest common factor and you're comparing between 2 numbers, what we're going to do is compare prime factorizations. It's not really a step. That's just a prerequisite. Compare prime factorization, which is what? That's the tree things we were just doing, right? We're going to compare prime factorization, and we're going to take the smallest option. This is where the confusion occurs, y'all. We're looking for the greatest common factor, but once we start comparing these numbers, you'll see what I mean in a second. Right now, it doesn't make much sense, but in a moment it will. We're going to be taking the smallest or the least option. The best advice I can give you to remember this is that it is backwards to what the first letter is. Greatest, you're actually going to be looking for the smallest. And hopefully this makes sense because you're dividing. Doesn't dividing make things smaller? It does say greater, and that's what smallest, that's what that says, guys, smallest. Doesn't dividing make things smaller, right? We are looking for the greatest, but I don't know. This is why it's confusing. Ignore the word greatest, basically, when you're doing the breakdown. The smallest option is what you want. Again, this will make more sense in just a moment. And the second rule is if no smallest, and you'll see what I mean by this in just a moment. If no smallest, take either one. Again, right now, this probably doesn't mean anything to you, but let's go ahead and just write the rules down, and then you'll very shortly see what I mean. So we're going to compare the prime factorizations of these 2 numbers. we're going to take the smallest option at any given moment. And if there is no smallest option, then we'll take whatever either option given to us. So think about what this means. Come up with the prime factorizations of 36 and 24 first. Do the tree, right? Take 36, get your tree. What did you get? Take 24, do your tree. What did you get? 36 should break down into 2 times 2 times 3 times 3. 24 should break down into 2 times 2 times 2 times 3. Validate that for yourself. Go back through and do the prime factorization trees for these. So far, we haven't done any GCF at all. All we did was break down 36 and break down 24. I didn't show the prime factorization, so go back and check it, make sure it makes sense to you. So first step in these is to compare prime factorizations, which is why I wrote it out like this. Here's the prime factorization of 36. Here's the prime factorization of 24. And notice I kind of put them over each other, 2s and then 3s and things like that. That's what I meant when I said compare prime factorization. Now, it says we're going to take the smallest option. And again, I know I've said this 2 or 3 times. I'm going to say it again. When you're doing the greatest common factor, this is not a mistake. You want the smallest of the options. So come through and look at your options. 36 has 2 2s in it. 24 has 3 2s in it. So this is what I meant when I said compare the prime factorizations. 36 has 2 2s. 24 has 3 2s. Which is the smallest option? Should we take 2 2s or 3 2s? The smallest option would be to take 2 2s, right? Because 2 is less than 3. So that is what we're going to do. I'm going to take these 2 2s here, and I'm going to eliminate the larger group. Keep or take the smallest option, the smallest group. It's not always a group. Could just be a single number. Looking at the 3s, 36 has 2 3s in it. 24 has 1 3 in it. So again, the same question. Which is the smallest option? Well, 2 3s or 1 3. 2 3s or 1 3. Well, hopefully, clearly, 1 3 is the smaller option. So we eliminate the larger group. And whatever is left is your GCF. So the GCF of 24 and 36 is 2 times 2 times 3, which if you want to multiply it out is 12. Now that one you might have been able to do in your head. And look, if it's reasonable, 36 and 24, and you say, look, man, I just knew that 12 went into that, and that was the largest number, I could buy that. I could buy that. But we're going to do an example or two in a minute, well, very shortly, where the numbers are big to where I'd almost really be suspicious if you said you did it in your head. So be aware, guys, if on the test or something, you do something and you claim you did it in your head, there's a strong possibility I might have you do it in front of me via Zoom. Not as a call out, but just more like, well, you know, that's a hard thing to believe, so why don't you show me? So be a little bit careful about doing things in your head. This is the way we're going to break down GCF. Keep those rules in mind because I'm not going to rewrite them on the next page. As you guys know, I don't have a ton of room here. So we got to be a little bit conservative with the paper. So again, GCF, GCM, or GCF, GCD, excuse me, I have a habit of saying that. GCF and the GCD. That's still what we're working on. Greatest common factor or greatest common divisor. It is the same thing. Whichever one helps you remember it better. I actually like greatest common divisor a little bit better because divisor helps me remember that I'm taking the smaller number. Just remember the steps. I'm going to throw it up here again. Compare prime factorizations. Take the smallest option. And if there is no smallest, we'll take either one, but we'll get to that in a second. So let's say I said find the find the GCF rather of 100 and 360. All right. So I've said find a GCF of 100 and 360. First step is to get the prime factorizations. That's why we went over that. It's critical because that's the first thing you have to do. You can't compare these really without doing that. So go ahead and start your tree and break down 100 and 360. I'm going to do it my way here. If you're stuck, follow along. But, you know, try to do this one on your own, I think. 100, I would use 10 and 10 maybe. You could use 2 and 50. It doesn't matter. 10 would be 2 and 5. 10 would be 2 and 5. 2 is prime, 5 is prime, 2 is prime, 5 is prime. So hopefully you agree that the prime factorization of 100 is 2 times 2 times 5 times 5. Write them in order because, again, we are going to be comparing them, remember. You don't want to have 2's laying all over the place and, you know, try to keep them orderly, you know, if you can. 360. Break that one down any way you want to with the prime factorization. I'll probably shoot for 36 and 10. 10 breaks down again, as we know, into 2 and 5. 2 is prime, so that's good. 5 is prime, so that's good. 36 breaks down into 9 and 4, which can keep going, right? 4 breaks down into 2 and 2. 9 breaks down into 3 and 3. So collect them all together and be careful now. 1, 2, 3 2s, so 360 was 1, 2, 3 2s, 2 3s, and 1 5. Be a little bit careful here, guys. Don't lose them as you go, right? Don't lose it as you go. So 1, 2, 3 2s, 2 3s, and 1 5, okay? Again, like I said, some of these are a little bit longer. You're not going to be able to do all of these in your head. Now remember what we're doing with the GCF. The greatest common factor, we actually want the least. So compare the numbers. We've got 2 2s here. We've got 3 2s here. So again, because we're doing the greatest common factor, ask yourself which is the least, which is the smaller group. That's what you want. So we will take the group of the smaller set, which is 2 2s. Now we come over here. We've got 2 3s, and there are no 3s at all up top. Again, think about what I'm saying. 2 3s down here, no 3s up here. So again, it's the same question. Which is smaller, 2 3s or no 3s? Well, no 3s, having no 3s at all is the smaller option, isn't it? So that's what we're going to take, meaning we're not going to take the 3s at all. Keep in mind, don't make this another rule. I said if it's smaller, that's what we're going to take. 2 3s is larger than no 3s, so we're going to eliminate it. We're going to take no 3s at all. Now we come on the 5s. We have 2 5s and 1 5, which is the smaller option. That would be just 1 5, meaning these are eliminated. So when we put our GCF together down here, we had 2 2s left over and a 5 left over, which is 20. So the largest number that divides into 360 and 100 is 20. Again, notice that these are smaller. Greatest common factor, the answer is smaller because you're dividing. Keep that in mind. It will help you remember. It's really easy to say, oh, greatest common factor. That number should be big. No, divisors get smaller. Be careful, guys. Be careful. All right, let's do one more here. I'm actually going to squeeze it in on this page because I'm kind of going to skim through the ugliness. I just want to do an example where we're not doing numbers like, 100 and 24 and things like that. I want to do a situation where there's, quite a bit of numbers. So let's say I asked you to find a GCF of 630 and 105. Now, again, I didn't say I'm necessarily going to ask you for the prime factorization. It is possible that you will be given the prime factorization already, and you will just have to know how to do the GCF. So, don't go into robot mode here. Pay attention. If you're given the prime factorizations already, 630 is these, 105 is these, well, you don't need to break them down then, right? So pay attention on the test. If you're given a problem where the numbers are already prime factored for you, all you have to do is the comparison. So let's go ahead and find a GCF of 630 and 105 using the same rules as we did a minute ago. What about the 2? Think about it. Am I going to take it or not? We have 1 2 versus no 2s. We are doing the greatest common factor, so we want the smallest choice, which would be no 2s at all. No 2s is smaller than 1 2. For the 3s, we have a choice of between 2 3s or 1 3, which is smaller, 1 3. We can't take none because the choice was between 2 of them or 1 of them, so we took 2 of them. So we took 1 of them. We're always going to take the least. The choice was between 2 of them or 1 of them. We took the least, so we just took the 1 3. Now, this is what I meant when I said if they're the same, take either one. Go back to the rules we said a minute ago. Throw it up here one more time. We said first take the smallest option when doing GCF, and then we also said if there is no small, oh, there goes my alarm. Sorry, guys. You turn that off. How rude. We said that if there is no smallest option, we'll take either one. So this is what I meant by that. Come back to the problem and look. For the 5s, there is no smallest option. It's 1 5 or 1 5. So take either one. It doesn't matter. We're not going to take both. We're going to take either one. I'll just take one of the 5s and the other one's out. Same with the 7s. If they're equal, you have choice between 1 7 and 1 7. Well, it doesn't matter which one you take. So the greatest common factor between 630 and 105 was 3 times 5 times 7, which is equal to 105. So it is absolutely possible to get one of the numbers back, because think about it. What are you saying here? You're saying, what is the biggest number that goes into 630 and 105? Well, 105 goes into both of them, and that's the biggest number, the greatest common factor of 630 and 105. So hopefully these examples kind of make it clear to you what I mean when I say take the smallest option. We took 1 3 versus 2 3s. And if there is no smaller option, 5 and 5, take either one. It doesn't matter which 5 you take because you're only taking one. It didn't matter which 7 we took because they're both the same. We only take one. So take a minute, go back to the examples. This can be a little bit confusing for people because this is not something you may have done before. And you might have done GCF before, but probably with numbers like 12 and 6. And you said, what's the GCF of 12 and 6? Oh, it's 6. I just did it in my head. We're going to be asking you to do bigger numbers like this. So you need to get in the habit of doing this with the prime factorization, okay? So take a minute, go back to the examples if you need to, make sure that makes sense. And then we'll go ahead and move into LCM here and wrap this up. Now, the good news is once you know how to do GCF, LCM is basically just GCF backwards, okay? So for real, take a minute, and if you need to, stop the video, rewind, and go back and do the 3 GCF questions we just did for examples. Because if you can do those, then once we do the LCM, it's going to be a lot easier for you because it's the same thing. The rules are just backwards, okay? LCM or LCD, they can be they're used, interchangeably, is the least common multiple. I'm going to stop right here and ask you something. Do you think that least common multiples would be bigger or smaller than the numbers you're asked about? You might say less, right, because it's least. Again, this is backwards. Greatest common factors were the least, and least common multiples are going to get bigger because of multiplication. It's really the last word in the phrase that tells you what happens. Greatest common factor. Factors are dividing, so it gets smaller. Least common multiple, multiples, multiplication makes things bigger. It's kind of confusing, I know. Another way to do it is just remember it's the opposite of whatever the first word is. This says least common multiple, so what that means is you're going to be looking for the greatest. It's very confusing because it's backwards. We're going to take the greatest option when we can. And just like the GCF, if no greater, meaning if neither of the number pairs is greater, take either one. So if you went through and you understood the GCF rules, these should be very similar. They're just literally the opposite. Instead of saying we're going to take the smallest, now we're going to take the greatest. And instead of saying, well, and then this one is the same. If there is no greater, then take either one. So again, this can be very confusing until you learn the rules. Once you learn the rules, they're just opposites of each other. This is something you're probably going to need to practice on until it clicks for you. So let's start off. Let's actually go back and use the same numbers that we were using for the GCF. Let's actually go back and do that. Might save you a little time because you don't have to break them down over and over again, but also so you can compare the difference in the methods. Okay, so the first one we did for GCF was 24 and 36, right? You've already broken these down, so if you don't want to do it again, that's fine. But I would encourage you, practice the breakdown, practice the prime factorization, get the trees, break them down. 24 should be 2 times 2 times 2 times 3 once you break it down. 36 should be 2 times 2 times 3 times 3 once you break it down. And again, that should be the same breakdown you got when we did the GCF of these numbers, okay? The breakdown, the prime factorization part should not change. The question is, how many 2s are we taking? How many 3s are we taking to make the LCM? Again, ask yourself, pop quiz, am I taking the least or am I taking the greatest? It's backwards from what it says. So even though it says the least, you're actually taking the greatest. So we have the choice between taking 3 2s and 2 2s. When we did the greatest common factor and we wanted the smallest pair, we took 2 2s. Now we are doing the least common multiple, which really means that you want the greatest of the pairs. So instead of taking 2 2s, I'm going to take 3 2s. Similar with the 3s, I have 1 3 versus 2 3s, which is the greatest option, taking the 2 3s. Remember, least common multiple actually gets greater. So the LCM for 24 and 36 is 2 times 2 times 3 times 3. And honestly, on the test, if you want to leave it like that, I don't have a problem with it. You don't necessarily need to go back and multiply these all together. If you want to, you can. 2 times 2 times 2 is 8, and 3 times 3 is 9. So this would be an LCM, a least common multiple of 72. And if you think about that, it makes sense, right? Just real quick off to the side here. If I took 24, list out the multiples. 24, 48, 72, so on. Now list your multiples of 36. 36, 72. Wasn't 72 the first one I came to? The least common. But sitting here doing this can be a real pain in the butt if these numbers are 105 and 630, like the problem we did at the end just a minute ago. So listing them out is not really feasible. This is the way you want to do it. You want to compare the prime factorizations, take the greatest. If there is no greatest, then you just take either choice. It doesn't matter, okay? So make sure you're cool with that. Let's go back and do those two examples we did with the GCF one more time. Let's do them with the LCM. The second example we did was 100 and 360. And I want, again, the LCM of 100 and 360. Remember, LCM means the greatest. First thing to do here is the prime factorization. Now, again, we've already done this, so I'll go ahead and just write it out what it is. We did this when we did GCF. If you need the practice, go back and do it again. There's nothing wrong with that. There's no shame in it at all. The students who go back and do the most reviewing are the students with the highest grades on the test. It's just simple as that. We already broke these down, so again, just to save time, we'll go back and rewrite them. If you want to, though, do it again. So that was what happened when we broke down 100 and 360. 100 was 2, 2, 5, and 5. 360 was 2, 2, 2, 3, 3, and 5. And again, the way we got those numbers was using prime factorization or the tree method, okay? So remember with LCM, just to bring the rules back one more time, we want the greatest option, and if there is no greatest option, we'll take either one. So go through and compare your numbers. You have the option between taking 2 2s and 3 2s. We are doing the least common multiple, which hopefully by now you realize means we want the greatest option, which is 3 2s. Now we move on to the next number pair, which is the 3s. You could do the 5s first. We'll just go in order and do 3s. I have the choice between 2 3s or no 3s. We want the greatest option, which is 2 3s. If it was GCF, we would take no 3s, right? And then to the 5s, we have the option between 2 5s and 1 5. This is the LCM, so we want the greatest, so I will take 2 5s. It's annoying, guys. I mean, I get it, the fact that you're doing the LCM and you want the greatest, and you're doing the GCF and you want the least. But that is, unfortunately, the way it goes. I'm not getting these backwards. That is the way they go. So the LCM, the least common multiple of 100 and 360, is 2 times 2 times 2, 3 times 3, times 5 times 5. The LCM will often be a very large number. And again, you are not required to multiply all that out unless the homework specifically says you have to, okay? Go ahead. If you're curious, though, it is 3,600. If you multiply all that out, it is 3,600, okay? So that's the LCM. Let's do one more. Let's do the big ugly numbers we did at the end with the GCF last time. We had, I believe it was 630 and 105. Okay, and again, we're looking for the LCM. I just keep writing that down so you'll have a reference. Least common multiple means we're going to want the greatest. Go back and get your prime factorization. You can either reuse the ones we did earlier when we did these numbers, or you can just redo it for practice. 630 is 2 times 3 times 3 times 5 times 7. 105 is 3 times 5 times 7. So what we're going to go do, hopefully now you get the idea, go through, try it, see what you get, and let's go, and then pause it and see if you get what I get. Or rather, sorry, pause it, do it yourself, and then go back and see if what you got matches what I get. So we'll start with the 2s. I have the option between taking the 2 here and taking no 2s here, right? This is 3, 5, and 7, no 2s down here versus 1, 2 up here. This is the LCM, so I want the largest or greatest option, so I will take the 2. 1, 2 is bigger than no 2s. Now we have the choice between 2 3s and 1 3, which is larger because we're doing the LCM, so we want the greatest option or the larger option, which would be 2 3s. Now, here we have the choice between 1.5 and 1.5. And this is what I meant, again, when I said, if there are no greater, take either one. 1.5 and 1.5, neither one of those is greater, so just pick one. It doesn't matter which one you take. They're the same number. Just take one of them. Here we have the option between 7 and 7. Again, neither is greater. 7 and 7, they're equal, so just take one. It doesn't matter which one. So your LCM for 630 and 105 is 2 times 3 times 3 times 5 times 7, which is an okay way to leave the answer. And if you multiply it all out, excuse me, you actually get 630, because 630 multiplies to make 630 times 1, and 105 multiplies to make 630. This is the least or the smallest number that they both can multiply to make. The way we found it was by comparing their primes and taking the largest. So the real danger here, y'all, is that you confuse when to take the largest and when to take the smallest. And the way you'll confuse it is because the names are backwards. When you're doing the least common multiple, you want to take the greatest. When you take the greatest common multiple, you actually are looking for the least when you're doing the comparison. One other thing I'll mention to you, there's a few word problems in the homework this time. Don't get panicked about them. They're either LCM or GCF. There's only two things in the word problems. If they're asking you how you could divide something up, that's going to be the greatest common divisor, or the GCF. If they're asking you, this occurs every 5 days and this occurs every 7 days, when will they meet up? Well, we're asking for the least common multiple, right? When will these two activities meet up? When will they multiply out to be the same? So if the homework is, if the word problem asks you to divide something up, you're talking about GCF. If it asks you to multiply things together or find out when things will occur at the same time, that's LCM. So just a quick way to tell, it's once you know if you're doing GCF or LCM, it's really just the same thing. Okay, so that's kind of a weird homework. Hopefully that wasn't too bad. Maybe the first one where the material might have been new to you. Maybe not, just depends on where you're at. Spend time with this homework, don't blow it off. It's one of those that students like to say, well, that one was easy. Once I learned how to do it, I blew through it. Yeah, and then on the test, if you don't know what you're doing and you get them backwards, it's gonna completely blow up in your face. So be careful. LCM, you take the greatest. GCF, you take the least. All right. Sorry about the alarm going off in the middle of the video, guys. I'm gonna have to do better about that. But if you have any questions, send me an email, and otherwise, I will see you guys in the next one.